Assalamualaikum warahmatullahi wabarakatuh. In this video, we are going to present our video assignment related to gas chromatography and high performance liquid chromatography. Here is our group that consisted of 6 members. First, INSYIRAH. Second, NURAISYAH NASUHA. Third, EYVA SEPHIA FILNEY. Fourth, Anisha. Fifth, me, ELLYSA. And lastly, NURUL FAAHIEMA. Experiment 5 is about the analysis of vanillin in white chocolate by gas chromatography. In the introduction part, I will explain about the principles, instrumentations, and vanilla briefly. Gas chromatography is a separation method that can isolate volatile gaseous mixtures from the differences in their boiling point or vapor pressure as well as polarity. It employs inert gases such as helium, nitrogen, and argon as mobile phase and a column as its stationary phase. This method works by injecting a sample into the injection port through an injector. The mobile phase carrier gas will be separated as it passes through the column as the stationary phase and cast in thermostat oven, which will then be detected by the detector. Data obtained is displayed and analyzed on the computer. The instrumentation for this method are carrier gas, sample injector, flow controller, column, detector, computer, and flow meter. The aroma of vanilla is derived from cured vanilla pods and varies according to the origin of vanilla beans. The flavor of vanilla in chocolate is perceived depending upon the kind of chocolate recipe to which vanilla extract is included. To offer a true character with a more pronounced vanilla flavor, vanilla extract is frequently blended to milk or white chocolate.
Next, we will move on to the next part, which is the methodology. Firstly, we will look at the sample preparation for gas chromatography analysis of vanilla extract. For the extraction, the liquid volatile organic solvent of dichloromethane was used. This organic solvent needed to be water immiscible and able to solubilize the aroma compounds. For the quantification, an internal standard was selected in order to monitor the extraction yield and to quantify the key components. Each vanilla extract were placed in an Erlenmeyer flask with an internal standard and a saturated solution to help the migration of hydrophilic molecules towards the organic solvent during the extractions. The solution was then placed on a magnetic stirrer after the addition of the extraction solvent. Last but not least, the mixture was then placed in a separating funnel and separated in order to analyze the organic part containing the compound of interest. That's all for the sample preparation, and we will move on to the next part, which is analysis.
Now I'm going to continue with the GCMS analysis. The analysis of volatile compounds was performed by GC using the GC6890 from Agilent Technologies in combination with the mass selective detector MSD5973 Agilent Technologies. The aroma compounds of vanilla were separated by using a DBFF-AP column, which is 30 meter times 0.32 millimeters times 0.25 micrometer from Agilent Technologies. The analysis conditions were optimized internally to have the best resolution on most of the key molecules. The oven temperature is set at 40 degrees Celsius and the temperature gradient is applied to 240 degrees Celsius. Next, helium was used as a carrier gas and samples were injected with a split ratio of 1:7. An electronic impact ionization source was used with quadruple mass analyzer operating in full scan mode. The aroma compounds were identified from the mass spectra using a mass spectral library, NIST Mass Spectral Library version 2.0, and an internal database.
And today I will present to you about the result and discussion for analysis of vanillin in white chocolate by gas chromatography. The vanilla extract that been used in the experiment are from Madagascar, Papua New Guinea, and Indonesia. Through GCMS analysis of vanilla extract, we can see that the amount of vanillin in all 3 extracts were almost identical. Next is gas chromatography, mass spectrometry, olfactometry, GCMSO analysis of vanilla extract.
From the analysis, we see that the phenolic group aroma chemical contained glycol and vanillin were found in all three vanilla sources. Furthermore, the vanillin was the most prevalent component in the vanilla sample tested by the Pillar Gallus 2015. Other volatile phenolic compounds, including glycol and 4-vinyl glycol, were found at significantly lower concentration. Following data of the vanilla extract using GCMSO, glycol and vanillin were found to have the maximum odor intensity for all three sources. Next is dosage of vanilla in white chocolate. From this table, we can see that the dosage of vanilla extract in white chocolate from Madagascar is 0.06%, while the dosage for vanilla extract in white chocolate from Indonesia is 0.1%, and the dosage of vanilla extract for Papua New Guinea white chocolate is 0.056%. Thus, the highest dosage of vanilla extract in white chocolate are from Indonesia.
Experiment 6 is titled as Determination of Vanillin in Vanilla Essential Oils by High Performance Liquid Chromatography. High performance liquid chromatography is a kind of column chromatography in which a sample or analyte dissolved in the solvent as the mobile phase is pumped at high pressure along a column containing packing material as the stationary phase. The retention period of the analytes, or how quickly it travels through column, is determined by the characteristics of the sample and solvent and the type of the stationary phase. As the sample travels through column, analytes with the greatest associations with the stationary phase depart the column the slowest, indicating that they have the longest retention periods. It travels through a detector, which provides a signal proportional to the amount of analytes coming from the column. This signal is transferred to and collected by an HPLC computer system, which the data displayed as chromatogram. The instrumentation utilized by this method are mobile phase reservoir, sample, injector, pump, HPLC columns that are analytical and guide column, detector, computer that displays chromatogram. Vanillin is a fascinating molecule for educational chemistry that is commonly included with baked items for its flavor and scent. Vanillin is produced from lignin containing aqueous fluid produced by acid sulfide pulping of wood. The preparation of vanillin is made by transforming eugenol derived from cloves.
Now I'm going to continue with the methodology for high-performance liquid chromatography (HPLC) sample preparations. All chemicals were analytical grade and deionized water was prepared with a molecule system. Standard stock solutions of vanillin with concentration of 1 × 10⁻³ and O2 vanillin with the same concentration in water were prepared. From these solutions, dilutions were made for the preparation of the calibration curves and separations. Dilutions were made using the Eppendorf and Finn pipettes. Next will be INSYIRAH to continue with the HPLC analysis.
Next, I will continue to explain on the high-performance liquid chromatography analysis. So, the analysis of vanillin in vanilla extract was performed by the high-performance liquid chromatography equipment consisted of a model 2150 pump and a VMW 2141 dual wavelength UV detector. The chromatographic separation was obtained from a light crossfur 100 RP18 and capped column from EMYLYA, Germany. Injections were then made with a model 7125 universal loop injector of 20 microliter. The reverse phase HPLC was performed at ambient temperature with an isocratic mobile phase consisting of a water methanol with the ratio of 40:60. The flow rate was 0.7 ml per minute. The mobile phase was then degassed by vacuum filtration to a 0.45 micrometer filter and spudging with helium. Data analysis was then performed using the in-house data analysis program DAX, or known as Data Analysis Expression.
I'm going to continue the result and discussion for determination of vanillin and vanilla essential oil by high-performance liquid chromatography. In this experiment, there are three methods involved, including UV-vis spectrophotometry, micellar electrokinetic capillary chromatography and high-performance liquid chromatography. For UV-V spectrophotometry, the UV spectra of vanillin and ultravanillin were determined, and the spectra of solution of 1.00 times 10 power of negative for molarity of vanillin and ultravanillin are shown in Figure 1. In this figure, we can see the difference of wavelength for vanillin and ultravanillin. The maximum wavelength for vanillin is 280 nanometer. Because the solution of vanillin in water was colorless and the vanilla extract was yellow, probably due to the presence of other absorbing components, the sample was analyzed with capillary electrophoresis and reverse-phase high-performance liquid chromatography, not with the UV-Vis. For mycelial electrokinetic capillary chromatography, capillary electrophoresis is a method to separate all components before they are identified and quantified. The mycelial electrokinetic capillary chromatography mode MECC was used with sodium rhodesium sulfate as a supertensor since vanillin is a neutral component. Figure 2 shows the electrophorograms for the separation of 6S pressure injections of a mixture of 6.00 times 10 power of negative for polarity of vanillin and ultravanillin and dilute vulture vanilla extract. We can see in A there is ultravanillin present, while in B there is no ultravanillin present. The isomer vanillin and ultravanillin can easily be separated, and vanillin can be determined in vanilla extract without any pre-treatment. For all determination, the sample solution were measured twice, and the average value was used to calculate the concentrations of vanillin. Table 1 shows the result of vanillin determination, the relative standard deviation and the regression coefficient, while Table 2 shows the concentrations of vanillin in vulture vanilla extract determined by various students with the separation technique HPLC and MECC. Reverse-phase high-performance liquid chromatography was used to determine the vanillin at a wavelength of 280 nanometer. Figure 3 shows the chromatogram for a mixture of 10.0 times 10 power negative 5 molarity of vanillin and ultravanillin and dilute vulture vanilla extract. A good agreement between MECC and HPLC value was obtained. We can see the ultravanillins are present in A but not in B.
Lastly, we move on to the conclusion of these two experiments. First, for analysis of vanillin in white chocolate chromatography experiment, in a conclusion, we managed to identify the component that present in the white chocolate, which is called vanillin. Vanillin were classed as a phenolic group aroma compounds, and vanillin was the most abundant phenolic compound. From this experiment, we also can determine the retention time of vanillin, which is 38.2 minutes. Next, for determination of vanillin in vanilla extract experiment, we can conclude that the concentration of vanillin can be easily determined in vanilla extract. By applying two analytical methods, it can be verified whether the student worked accurately. The result obtained with RP, HPLC, and MECC are similar and no internal is needed. Although different wavelengths are used in RP, HPLC, and MECC. For MECC, higher concentration are needed for standards and sample because of the very short optical path length. The difference between the measured concentration for vanillin are larger than could be expected from RSD values. This may be caused by errors made by diluting the bulk vanilla extract, which has a very high viscosity.